Hello statisticians, today we're talking about inference for categorical data, specifically a chi-squared two-way table test, meaning that we have two different things that we could do, homogeneity, which we're going to talk about, and independence, which we're going to talk about. Both of them usually start with a two-way table in the problem. So a goodness of fit test, remember from last time, what does that look like? That is one population of interest and one categorical variable. That means you're trying to decide what the distribution of several hypothesized proportions are for a certain population of interest. I go and I ask a sample of my population for one question, and I want to know what does that distribution look like. So that's where we say category 1 is P1, category 2 is P2. I think 20% of my results are category 1 and 30% of my results are category 3. Remember, it's called a goodness of fit because our sample isn't going to match exactly what we believe is true about the population. But we want to know, how good does this fit that proportion? Could this variation have happened by chance alone? So we use the chi-squared value for that. The chi-squared value, remember, is observed minus expected. Your chi-squared value is part of a right-skewed distribution, and the p-value associated with your test is the area to the right of that chi-squared value. A chi-squared homogeneity test is one of the two-way tests. One of the things you want to look for is that there are two populations of interest and still just one categorical variable. What we're looking for is we're trying to see if the distribution of those proportions of that variable is the same across the two populations. Like saying if there's no difference in the distribution of favorite flavor of Star Sours candy, from our example yesterday, across the populations of all adults and of all children. Or maybe there is a difference in the distribution of favorite flavor of Star Sours candy across the populations of all adults and all children. So I'm not specifically looking for the proportion of red to be 20% and the proportion of blue to be 30%. What I want to know is the proportion of red equal to the proportion of red in the other category, in the other population? And is blue proportion equal to the blue proportion? And is the green proportion equal to the green proportion for both populations? The other kind of chi-squared two-way test also has two of something. In this case, we have two variables, but we only have one population. So instead of saying, is this one variable, say favorite flavor, the same for adults and children, one variable, two populations, we only have one population, but we have two questions that we're going to ask, two pieces of information we're going to collect from that population. So we're trying to see if there's an association or dependence between those two variables. Are the two variables independent or are they dependent in that population? For example, there's no association, they're not connected, they are independent between iPhone ownership and favorite color in the population of Avon High School students. Or maybe there is an association. If there is an association, we would expect those variables to be dependent. And if there's no association, we would expect those variables to be independent. Now, mathematically, in order to be able to do a chi-squared test for homogeneity or for independence, you've got to be able to calculate expected counts from a two-way table. So I have a two-way table over here, and I want to answer the question, are soccer players more likely to get concussions than other types of individuals? So this is one variable, it's the number of concussions, and even though that sounds like a discrete random variable here, we're going to be using it categorically. We've got 0, 1, 2, and then more than 3 or more here. Okay. We also have three actual populations. We've got soccer players, non-soccer players, and non-athletes, and we've sampled from each of those populations. And we want to know if the number of concussions, if that distribution is the same for each group or population, meaning that there are more soccer players here than there are non-athletes, but is the percentage who got three or more the same all the way down for all three groups? Is the percentage who got 0 the same all the way down for all three groups? This is a chi-squared test for homogeneity because we're comparing one variable, number of concussions, among multiple groups. So the expected counts for a two-way table, and I have my lovely little thing ready here of soccer players, non-soccer players, and non-athletes, and I'm looking for expected counts. We're just going to talk about 0 here for a second. So if the proportions are the same across all the categories meaning soccer players, sorry, across the populations, soccer players, non-soccer players, and non-athletes, we would expect the same proportion of each group to have 0 concussions. So if I take 0 out of the grand total, that's 158 out of 240, I end up with about 66%, which means about 65.83 or about 66% of each group should be 0. For soccer players, 91 soccer players, about 66% of that, and about 66% of non-soccer players, 96, and about 66% of 53 soccer players. And these give me my expected counts. I'm going to go ahead and put those in as my decimals. So I would expect to see 59.9, 63.2, and 34.9. And remember, it is fine to get decimals in those expected values. So to compute the expected counts, if you want to do this for the whole table, what you're going to do is you're going to take the expected count for any cell in the two-way table, and you're going to take the row total times the column total divided by the grand total. So for example, for soccer players, the row total is 91, the column total is 158, and the grand total is 240. That gives me the expected value of 59.9, and if you check, that's what we got when we did this using logic. So that's my expected count. Now, if you can use a chi-squared, then you're going to also need degrees of freedom. Degrees of freedom also works a little bit differently in a two-way table. So for a two-way table, because we have two different dimensions to this, we're going to make our degrees of freedom, instead of being categories minus 1, basically it's categories minus 1 for the columns and categories minus 1 for the rows. Or in other words, it's rows minus 1 times columns minus 1. And notice that the rows and columns, it doesn't include any of those totals. Total is just something that we use for ourselves. So here we go. So degrees of freedom. So I would take 3 minus 1, that's the number of rows excluding the total. And we would take 4 minus 1, that's the number of columns. Multiply that together, and this would have our degrees of freedom of 6 in this problem. Okay, so for example, a random sample of 1,200 men and 1,000 women who work in downtown office buildings were asked, are you a fan of the Indianapolis Colts? Find the expected counts and the value of chi-squared for the chi-squared test of homogeneity. Now, this is a homogeneity test because I've got two groups, men and women, and I'm curious about whether men and women are fans of the Indianapolis Colts equally. All right, so in my Scratchpad then, I'm going to open up my calculator and I'm going to take the row total times the column total divided by the total total. That gives me the amounts for yes and male, and then female and yes, okay, those two values. I'm going to do the same thing for the nose, row total times column total divided by total total, and then the same for females. And I'm going to have those values. So I've got my expected counts in there. Now I've got my expected counts. I'm going to find my chi-squared values. So remember, we're going to take the observed number minus the expected number squared divided by the expected number. So males, there's my 1,100 minus the 1,118.18. Okay, I'm going to square that and then divide by that total. And if you do that for each of those values where you're matching up each of the cells, observed minus expected divided by expected, and you're squaring that numerator on that, you end up with 7.42927. That is your chi-squared value. And you can see that I did this in my calculator to get this number. So the degrees of freedom associated, this would be rows minus 1 times columns minus 1. Remember, we're only looking at the categories of these two measurements that we're taking here. We're not these two characteristics, we're not looking at the totals when we do this. So there are 2 rows, yes and no, and there are 2 columns, male and female. 2 minus 1 times 2 minus 1, that's 1 times 1 or 1. So my chi-squared value is 7.439. Oh, I wrote that wrong. 7.430, isn't it? Ah, yes. Or maybe I should say 29. Maybe that's what the mistake is. Yes. If it wasn't a typo, would it really be one of my videos? There we go. With degrees of freedom equal to 1. All right, so when we go to run a chi-squared test for homogeneity or a chi-squared test for independence, we're still going to run phantoms, kind of. Our hypotheses are going to be written in words with no variable notation. So there's no parameters to define, and so we're going to skip this step. So for chi-squared tests of homogeneity and independence, we're basically doing phantoms. Now, those hypotheses for homogeneity, the homogeneity is basically saying that the distribution of my variables are the same across my populations. So I would say there's no difference in the distributions of my variable across the populations or treatments. You want to make sure you say those in context. So you want to say the distribution of what is my variable, and you want to make sure you address what those populations are. Okay? The independence test is when we're actually testing for association or for independence. So you're going to write out there's no association between the 2 categorical variables in that given population. And again, you're going to do that in context. Or you could say the 2 categorical variables are independent. Your alternate hypothesis is that the 2 categorical variables in the population are associated, or you could say they are dependent. For the assumptions and conditions, randomization is still there. If we're talking about the independence of 2 variables in one population, then that should be collected from a random sample. Homogeneity is comparing 2 groups, so you could be taking either 2 random samples or a stratified random sample, meaning that you randomly sample from the men and you randomly sample from the women, or you randomly sample from some other group that shares a common characteristic. So one sample essentially representing 2 different populations because it's stratified. Or your 2 groups could come from a randomized experiment. The 10% condition is still there. If you're sampling without replacement, you need to make sure your sample size is less than 10% of your population size. And then finally, large counts, same as yesterday. You need all those expected counts to be greater than 5. Okay, for the NTO, the name of the inference procedure will be a chi-squared test for homogeneity or for independence. And you want to be careful because in your calculator is going to say chi-squared two-way test. But you don't want to write that down. Both of these are two-way tests, but you need to make sure you use the right word, either homogeneity or independence. You're going to write down your test statistic and your degrees of freedom, which is that chi-squared value. Remember, your degrees of freedom is a little bit different with a two-way table. That's rows minus 1 times columns minus 1. You're going to get that p-value and you're going to write it down. And remember, the chi-squared and the p-value are most of the time going to be pulled straight out of your calculator. You're going to make a decision about the null hypothesis. You're going to make sure you state that linkage to the p-value and the decision, and you're going to state your conclusion in context regarding that alternate hypothesis. Remember, that means that your first option is, since the p-value is less than alpha, I reject the null hypothesis. There is convincing evidence to show whatever ha was, and you want to state that ha in context. Option 2 would be, since the p-value is greater than alpha, I fail to reject the null hypothesis. There's not convincing evidence to show ha in context. All right, so here is an example. Medical researchers enlisted 90 subjects for a double-blind experiment comparing treatments for depression. The subjects were randomly divided in 3 groups and given pills to take over a period of 3 months. Unknown to them, one group received a placebo, the second group received a natural remedy, St. John's wort, and the third group received a prescription drug called Posrex. After 6 months, psychologists and physicians evaluated subjects to see if their depression had returned. Is there evidence that the treatments were equally effective? Use the 1% level of significance. All right, so we need to identify what are the variables and what are the populations. So let's just start right here. This population, we have 3 groups. My first group is placebo, the second is St. John's wort, and the third group is Posrex. So those are my 3 groups, and this is an experiment, it looks like, because the subjects were put into these these 3 groups assigned by the researcher there. Okay, so if those are my groups, then the variables that we have here is the group is the kind of medicine they get. That's the explanatory variable, sorry. And then my response variable is the thing that I'm measuring, so that is whether or not depression has returned or not. So the other thing we want to think about here, so we have one variable, basically, we've got this variable we're measuring, and we have our population, which is multiple groups. I've got 3 groups here. What does it mean for the treatment to be equally effective? Okay, so if the treatments are equally effective, then what we would expect is that if it doesn't really make a difference if you're taking a placebo or St. John's wort or Posrex, what we're really saying is that the rate of depression returning should be about the same in all of these groups. Okay, and the no sign of depression should also be about the same. If one of these treatments actually does improve, we would expect, if it's more effective than the others, we would expect more improvers proportionally in that group. All right, so this is a chi-squared homogeneity test. We're measuring one variable over multiple groups. All right, so the null hypothesis, the distribution of the proportions of depression returned and not returned, that's my variable, is the same across all the treatments. My alternate, that's basically saying the treatments are equally effective. And my alternate hypothesis is that the distribution of the proportions of depression returned and not returned, so the proportions of my variable, of my categories here, is not the same across these 3 groups, across all treatments. That's like saying the treatments are not equally effective. We think that the null hypothesis is false. We believe that one of these treatments is probably more effective than others. All right, so assumptions and conditions. So subjects were randomly divided into 3 groups, so there is random assignment to treatments. That is stated. The 10% condition is not necessary, so since we're not sampling with replacement, I don't have to check that one. That one can just go away. And the smallest expected count. Now, why am I checking the smallest expected count? Well, I really need to show the work for this. Remember, anytime you're checking expected counts, you ought to show the work. So I'm going to figure out what's my smallest row number, what's my smallest column number, wherever those intersect, and these are the same, so it wouldn't really matter. That's going to tell me where my smallest expected count is. All right, so here's the deal. I checked the work for this one. Row total times column total divided by total, that's 10, okay? I could go through and find all the rest of them now, and I probably should, but I'm not going to do all of the work written down. I'm just going to check that smallest expected count, and I'm going to show that work. Okay, the other counts I'm going to put into there, but I'm just going to do those in my calculator. Now, if the smallest count is greater than or equal to 5, then all the expected counts must be greater than or equal to 5. And so I'm going to write all expected counts greater than or equal to 5 and see my table where I wrote those counts. Look at me checking my answers. All right, so we're going to perform this chi-squared homogeneity test, which means we need the test statistic, the chi-squared value. The degrees of freedom would be rows minus 1 times columns minus 1. All right, rows minus 1, there are 2 rows and there are 3 columns. So 2 minus 1 times 3 minus 1, that gives me degrees of freedom of 2. 1 times 2 is 2. And I need to get the p-value. Now to do this in your TI Inspire, I have the instructions written right here, and I'm going to go through those steps one at a time. So if you've got your TI Inspire, you're going to want to maybe pause the video and do each step with me. All right, so first off, I'm going to go to a new document and create a calculator page, or you can use the Scratchpad. It doesn't matter as long as you're in a calculator page. So calculator page in a document or a Scratchpad. And then what we're going to do is while you're in that calculator page or Scratchpad, you're going to have to create a matrix to enter in your observed counts. So what you're going to do is in that Scratchpad, you're going to press menu. Sorry, in the new document, you can go menu, matrix, create a matrix. So this is an optional step, and it's actually easier, I think, to do this instead. So these are the directions I'm actually following. So there's multiple ways to do this. There's a little button and it's next to number 9. Okay, and you can see I've got it circled here. If you press that, it will bring up some very interesting little shortcuts here, like a fraction and a radical, etc. But one of the things you want is this little 3x3 matrix, and you can see I have it identified there. That is the create a matrix menu, and if you pick that one that's 3x3, then it will actually prompt you to how big do you want this to be. So we want a matrix that has 2 rows and 3 columns. 2 rows for the actual data and 3 rows for the actual data. The totals do not go in here. All right, when I hit OK, it's going to bring up this 2x3 matrix, and I'm going to type in my expected counts. And then you're going to hit enter. Now, once you've got that entered into your calculator, it's saved in the answer, like the last answer. It's saved. So hitting enter. So I entered. I'm going to go back again. So I created my matrix. I typed in my numbers. I hit enter. You can see that's over there. My cursor is now in the bottom left right here. While I've got that cursor there, the next thing I'm going to do is I'm going to press Menu, Statistics, and Stat Tests. And I'm going to pick the one that says ChiSquared Two-Way Test. Now the ChiSquared Two-Way Test, when you select that, it's going to bring up a little thing that says, where is your observed matrix? Or what is your observed matrix? So what we're going to do is we're going to press Control and the negative key. And above that it says Answer. By pressing Control Answer, it will paste the last thing that we entered into our calculator into that spot. And the last thing that we entered into our calculator was the matrix of observed values. So by pressing Control and the minus key, I'm actually able to paste that answer into that spot. It just says ANS, answer. But what it really is this matrix that I just entered into my calculator. Once you've got that there, you're going to press OK. And it's going to bring up this chi-squared two-way test results. You'll see our chi-squared value and our p-value and the degrees of freedom. So there's our test statistic. There's our obtain the p-value. Okay, so that's very useful for our test. Now the other thing that's kind of exciting to me is right here is that it says expected matrix, but you can't see it, right? So if you were to want to actually see those expected values, you can actually press the variable button, VAR, and select the expected matrix. When you do that, it'll bring up the expected value matrix as well. And if you notice, those were the same expected values that we got when we did these by hand. So I want to go back to that check of those large counts. So I said, check the smallest one and then write in the rest. So in theory, you could check the smallest one, confirm, show your work, plug all the numbers in, confirm that it's greater than or equal to 5, run the rest of your hypothesis test, and at the very end, you can take these numbers, copy them into your table so you don't have to calculate them all by hand. And that's just for time-saving technique. All right, so our chi-squared homogeneity test had a chi-squared value of 8.4 and a p-value of 0.015. Okay, now the alpha value provided to us in this example is 1%, which is definitely our p-value is greater than 0.01 here. All right, so since the p-value is greater than alpha, I fail to reject the null hypothesis. Remember, the null hypothesis said that the distribution was the same or the treatments were equally effective. The alternate hypothesis is the one that shows that the distributions are not the same. The treatments are not equally effective. So since we failed to reject the null hypothesis, it means we do not have convincing evidence for Ha. So there's not convincing evidence to show that the distribution of the proportion of depression returned and not returned is not the same across all the treatments. Remember, that's the ha statement. I do not have evidence to support ha. So we cannot show that the treatments were not equally effective for people like those. Okay, so again, this statement always refers back to that alternate hypothesis. So you want to be really careful here, because what you want to say is, so it looks like the treatments were equally effective. Oh, okay, yes, but we never, ever, ever accept the null hypothesis. In statistics, we just don't do it. So if you can't reject the null hypothesis and say ha, you haven't proven that the null hypothesis is good to go. You haven't proven that they are equally effective. You just haven't proven that they're not. So be real careful with that. All right, one more example. A survey was taken to determine if there's a relationship between students having a landline telephone in their home and their school level, elementary school, middle school, high school. A random sample of 250 Leahyville Community School Corporation students, LCSC, from grades K to 12 produced the results in the table. Is there evidence that the school level and having a landline telephone at home are associated? Are associated. Use a 5% level of significance. All right, so we took a sample of 250 students and we asked them 2 questions. So we have one population, we have 2 variables. The first variable is the school level, and the second variable is, do you have a landline telephone at home? And associated means that there's a relationship between those. For example, maybe you're more likely to be a high school student if I know that you have a landline telephone at home, or maybe not. So associated means dependent in this case. So dependent. Are these dependent or are these independent? So we're going to do a ChiSquared test for independence. All right. So here we go. My null hypothesis is that my 2 variables, ownership, yes, no, of a landline telephone and grade level are not associated. That means they're independent. If they're independent, then the proportions should be the same of yes and no's across the categories of that other variables. So it's similar to the test for homogeneity. It's just the way you set up the null hypothesis is a little different. My alternate hypothesis is that my 2 variables are associated, that they are dependent. All right, so assumptions, random sample, stated. 250, less than 10% of all students in this corporation? Sure, reasonable to assume. My smallest expected count would be the 100 is the smallest column, and 100 the smallest row, and 75 is the smallest column. So we're looking at this elementary and no section here, or I could have picked middle, it wouldn't make a difference. That would be row total times column total divided by total, that's 30. If the smallest expected count is greater than or equal to 5, then all expected counts will be greater than or equal to 5. And I went ahead and wrote the other expected counts in the table. Now you could do those by hand in your calculator, or again, you could maybe write them in at the end after you run your chi-square test. Now the commands are going to be exactly the same as the last example. We're performing a chi-squared independence test. We need chi-squared. Again, in this problem, I still have 2 rows and 3 columns of actual data, not including totals. So my degrees of freedom are going to be 2 again in this test. All right, so in your Scratchpad, you're going to press that key next to the 9. That's going to open up the possibility of this shorthand here. You're going to pick the one that looks like a little 3x3 matrix. Okay, it's going to have 2 rows, okay, and 3 columns for the observed counts. Okay, remember, we don't include totals in that. You're going to type those numbers in. So I'm typing in the observed counts. Okay, I'm going to hit enter. That's going to save it as my last answer. While I'm still in this Scratchpad, I'm going to press Menu, Statistics, Stat Test, and chi-squared 2-way table. That's going to give me this thing that says, where's the observed matrix? So we're going to press Control and answer. That's going to paste that matrix into that spot. So my chi-squared 2-way test has my answer there. I'm going to hit enter, OK. And it's going to give me the results. You can see an enormous chi-squared value here, 82.9. That's crazy high. And the p-value is times is times 10 to the negative 19th. That's crazy low. All right. So again, if you want those expected values, you can press the variable key and see what the expected values are. Same thing I got when I calculated it by hand. All right, so back here, my chi-squared value, that crazy 82.94, my p-value, 9.746 times 10 to the negative 19th. I'm going to write that as 0.000 to 3 decimal places. Okay, so since that p-value, essentially 0, is less than our alpha of 5%, I'm going to reject the null hypothesis. That means that there is convincing evidence for Haas. Remember, Haas said there is an association between these two variables, the ownership of a landline telephone and the grade level for all students at Leahyville Community Schools. Okay, now if there is an association, that means that these variables are dependent variables within this population of students. All right, so which test do I use? So all of these are for categorical data. So you always need to start there. Do I have categorical data? Yes. Chi-squared goodness of fit test is for a set of sample proportions for one population. So you have one population, you have one variable. Chi-squared for homogeneity, you're comparing two or more independent populations, but you still only have one variable. So one variable, one population up here. For a chi-squared test for homogeneity, you still have one variable, but you're comparing the distributions against two or possibly more populations or treatments. Buzzwords you want to look for. Homogeneity tests are things that ask you to check, were these the same? Were they different? Were they equal? Have they changed since we looked at them last time? And finally, independence. To test for independence of two categorical variables, you have two variables this time, but only one population that you're checking that in there for. You're looking for words like, is there an association? Are they dependent? Are they related? Is there a relationship between these two variables? You're going to test for that independence. Okay, remember that each set of null and alternate hypotheses are pretty much going to be unique to these problems. So for my goodness of fit test, I actually have a string of actual proportions, like P1 is 25% and P2 is 50%, etc. My alternate hypothesis is basically that the null hypothesis is false. At least one or at least two of those hypothesized proportions are incorrect. In your calculator, this runs as the chi-squared goodness of fit test, and you're going to put your data in a spreadsheet. That spreadsheet is going to have an observed column and an expected column. Okay, for the chi-squared test for homogeneity and the chi-squared test for independence, both of these have the same test. This is a chi-squared two-way test in your calculator, and you're going to use a matrix to type in those observed counts. Remember that homogeneity is saying that the proportions are the same for all the populations, whereas the independence test is basically saying the two variables are independent in this one population. So here's what you need to be able to do today. You need to be able to say, I can determine the degrees of freedom for a chi-squared goodness of fit test. That's K minus 1, categories minus 1, and for two-ways test. That's rows minus 1 times columns minus 1. So you need to know when I need to use which degrees of freedom. You need to be able to calculate the expected value for each category of a goodness of fit test or in a two-way test situation. So remember, with goodness of fit, you're just taking n times each of those sample or those hypothesized proportions. For a two-way test, you're taking your row total times your column total and dividing by your grand total to find those expected counts. You need to be able to compute the value of chi-squared by hand using the formula or be able to find it in your calculator. You need to be able to perform all the tests of phantoms. Remember, if you're doing one of the two-way tests, it's just phantoms. for chi-squared tests of goodness of fit, homogeneity, and independence. And then finally, you need to be able to recognize which type of chi-squared test is needed based on the context of the problem. So you need to be on the lookout for words like associated, or are these proportions the same? Or does it look like there's no preference uniformly distributed 100% across all my categories? You can do this. I believe in you.